Welcome to Brain Vision.
So in problem 43 here we have a beam, and now we have basically it's supported on a ground where we're assuming that the reaction here is uniformly distributed. So what we need to do is figure out the total force acting on the upper part of the beam, and then divide that by the total length of the beam to figure out what this distributed load is here. And so in this problem, they only gave us, they didn't give us absolute actual numerical values. So we just know that this has a magnitude of W, and that would be some kind of force per unit length. Same here, and then this would have units of force. And we're told that P equals A times W, which would have the units of force. So we know that this distributed load has a value of 3/4 W. So this would be 3/4 W, and then W would be again a force per unit length. So we take cuts in these regions here, okay, where things change, and we see that there's zero shear forces at the end, and also zero moments at the end. And so in this region here, we have basically two counteracting distributed loads. So we wind up with a net slope that's negative here. So we wind up getting down to minus 0.25. And what I've plotted here is the shear force divided by A times W. So as A increases or W increases, this value would actually increase. So here the value would be V, the shear force would be minus 1/4 A times W. Now in this region we have just the reaction from the ground, and so we wind up with a positive slope, and we wind up back up here at 0.5, so V over AW is 0.5. Since P is A times W, then we jump back down here to minus 0.5. So this gives us our maximum absolute value. So that occurs right here in the center. And then over this region, we have a positive slope again, so we'll come back up. And then over this region, we have a negative slope because this is bigger than this, and we come back down to 0. So again, another good check on this is symmetry, because we can see we have symmetry in this problem. So that fair check confirms that. And so then for the moment diagram, again, we have linear regions everywhere, so everything is going to be quadratic functions. I wrote down what these kind of are. So again, I'm plotting here m over a squared w. So the bending moment would be whatever this value is times a squared times w. So in this region we have minus x squared over 8a squared, and again this I'm plotting for x, I'm plotting x over a. So that's why we just end at 4. When x over a is 4 is at the end of this beam. So here we have minus x squared over 8a squared is this parabola, and then this one here is given by this formula here. And we can see that the bending moment is going to be 0 at this midpoint here, and we can figure out where this maximum occurs, because we know the maximum, the extrema of the moment occurs whenever the shear force goes to 0. So at these 2 points here, and that is at turns out to be 4/3 a. So 4/3 a is here, and then again over 2 2/3 a is here. So those are where our two maximum occur, and it turns out to be a squared w all over 6. So again, as a increases, we actually get larger and larger bending moments because the length we're getting. So it's a quadratic function of a, so we're getting a lot of extra bending moments if we increase the length of this much more rapidly than if we increase the weights here.